Yeah, so this is the data, okay, in SPSS, and we've already seen the scatter for the data sets, this same data set in Excel, okay? That is the same data set we saw earlier in Excel. Now, what we're going to do here is to conduct some investigations on or correlation, okay, analysis, okay? So what you do is you go to analyze, as you can see, okay? And then go to correlate. Once you do that, you can go to bivariate, yeah, and run the correlation for all variables. So of course, here is not part, but we can look at the 4 variables we are dealing with, right? And since the data is continuous, we can use the PSA's correlation coefficient, okay? And then of course, we can test, that's a test of significance with 2 tail over here. Okay, so once you select OK, the output will be displayed. Let's go to output. Okay, so I'm sure you can see my output. Now, if you look at this is interest rate and CPI, like we saw earlier in Excel. Okay, we had a negative correlation between the interest rate and the CPI. Okay, and then we also had a positive correlation that is indicated by, okay, negative 0.508, okay, which is a moderate negative correlation between what the CPI and our interest rate. Okay, the same with IR, which is interest rate with unemployment rates. We are getting a positive value for that. And then interest rate and GDP, we are getting a negative value for that. Okay, good. And like we said, the next important thing to look out for is the significance. Okay, it is necessary for you to check the significance of the correlation coefficient that is, okay, estimated for, right? So that is checked with the p-value here. Okay, so we compare the p-value, which should be less than, the p-value is your sig 2 tail. Okay, so the p-values, these are the p-values. These are p-values. Okay, these are the p-value. Of course, the table is the diagonals place it. So the other half is just the, let me say, reflex image, okay, of the upper half of the table. Okay, good. So our standard of comparison is your p-value should always be what? P-value should always be less than your alpha value, okay, which is 0.05 in this case. So the default is 0.05 here, okay, 0.05. And you can see that the test was conducted on 2 levels. So correlation at 0.05 and correlation at 0.01, okay? So we need to compare. Once your P is less than 0.05, then the correlation coefficient is significant, okay? Good, which is automatically flat. But as you can see, this is not a significant correlation, okay? Even though we have a moderate correlation here, this is also not significant, okay? It's also moderate, but not significant. This is negative, not significant, okay? But when we go to CPI and the employment rate, okay, that is a statistically significant correlation over here, okay? CPI and unemployment rate, we have negative correlation here. And we have a positive correlation for CPI and the GDP. Okay, CPI and the GDP. Of course, we should have probably used GDP per capita. Okay, good. That would have been a better measure for this analysis or this test. Then also unemployment rates and GDP. Okay, also we can see some significant relationship over here, which is negative, right? So once again, the data we're having here is still confirming the same pattern we saw in earlier lecture by Dr. Said. Okay, good. So if we are to talk about significant correlations, then we are talking about CPI and unemployment rate, CPI, GDP, and then what unemployment and GDP. Okay, good. Now in terms of making inferences and applying them in the practical sense, right? When I ask you to investigate the relationship among the variable, you don't just conclude that there is negative relationship at 5% significance level, and which means that this is related to that. No, after you have made your statistical conclusion, you also need to come out with practical implication. Okay, so you can see in the midterm, I ask you to explain a possible reason for the observed correlation or the observed relationship among the variable. I want you to be more practical over there when I ask such a question. Don't give me statistics. Okay, so for example, unemployment rate and GDP, we have seen the relationship between them practically. Why GDP is negatively correlated with unemployment rates, okay? Because once the unemployment rate goes high, right, it means that lesser people are what? Employed. And if less people are employed, yes, there are so many ways in which it is going to influence what? Their GDP, okay? Good. In terms of getting even the capital to even set up businesses or to do something on their own, which will also generate goods and services, becomes a problem once they are not employed. So it will have a negative effect on the GDP of the individuals. And again, from another level, if people are not employed, then it means that we don't have the resource, okay, to even generate those goods and services within particularly the non-oil sector, okay, which employs over 60%, okay, of our youth, right? So if unemployment is on the low side, then it means we have fewer people working, which means that we will not be able to generate those resources, those services and goods we need to export or we need to sell out there to finally accumulate toward our GDP. Okay, good. So that is an explanation in real life sense, which you go into your discussions, assuming you are doing something like this in your research, and you come out with this conclusion. This final discussion should be part of your discussion session where you go beyond the statistical analysis or the statistical findings you just found. Okay. Now again, something like CPI and yes, something like CPI and GDP, okay, or CPI and unemployment rates, right? We need to think through carefully, right? Because when we talk about CPI will essentially give us our inflation rates, okay? And if inflation rates are, CPI and inflation are always in the same line, right? So if inflation rates are going up or CPI is going up, inflation will be going up. If inflation is going up, then it means that the amount of money you need to purchase the same good becomes devalued. Or let me say, if CPI rises by, let's say, 50%, the current CPI is inflation, sorry, the inflation rate now is about 52%, okay? Good. But you see the previous year month's inflation was 56. So which means if you had 100 cedis two months ago. Last month you need 153 cedi to purchase the same product in the general, okay, on the average, let me put it that way. And then in the next month, which is the current month, it is 52 of the 156, not of the 100. Okay, so that is going to be around 72 cedi in addition. So you need almost 220 Ghana cedi to purchase something which you were purchasing 100 cedis earlier. So which means that the value of your money is already gone down, right? So even though in terms of creating business, it becomes a problem because your capital is devalued by reason of the rising CPI. So as CPI is increasing, okay, there is devaluing of your currency, which will also affect, okay, you, many in terms of creating platform for people to even be, or creating jobs for people to be employed. So that is one implication, or let's say practical means by which this relationship will make sense. Okay, good. So we expect you to connect the various indicators. Why are we seeing this kind of relationship? Okay, good. Another interesting one, which something I find quite interesting, is the CPI and the interest rates. CPI and interest rate, which is not significant. Of course, we saw from the scatter that, let's plot the scatter again. Okay, if we need a scatter, you go to graphs. Go to graphs. Then you go to chart builder. Go and click on, let me clear the screen first. You go to scatter, okay, click on scatter, and we want a simple scatter, okay. Either we take a simple scatter or we'll take a scatter matrix, okay, for all the data sets, right? So, but for now, let me use a simple scatter. So let's look at inflation rates and CPI, okay, and then okay it. Now we saw the same output in we saw the same output in Excel, okay, where we saw the negative slope, okay, for the line. But you can see that the points are quite dispersed. So even though they are moderately correlated, this relationship is not significant. And I'm saying that it's quite interesting, okay? From an economic point of view, we expect that while CPI is going up, okay, inflation rates will go up, and for that reason, okay, we should expect the interest rates to go up, right? Good. But you see, in another sense, to interest rates and inflation rates are directly related, okay. But if you have a situation where the observed data CPI is dropping, then it means that inflation will be dropping, and yeah, of course, we should expect the interest rate to come up. So, and I'm wondering the source of this data. I think we need to check it again, because if we check CPI in Ghana for the number of years we are talking about, and the interest rate, they've always so high. It's rather not coming down, okay? So it's quite surprising to have this data set. Let me see who I picked this data from. I don't know, but I'm sure it's coming from, that should be coming from Nura, okay? Nura, you said you had this from Microtrends. That's quite an interesting data you have there, okay, which really doesn't make, um, I mean, it really doesn't reflect the patterns. Interest rates have gone high. Eh? Interest rates have gone high in the country, okay, as the CPI was going up. So, which means that we can flag this interest rates we are having from this data. We need to go back and go and check whether this data is actually what it's supposed to be, right? But naturally, like I'm saying, the data itself and the relationship you are observing should be able to tell you should be able to explain what is really happening, okay, within the country, okay. Good. So if you are seeing a pattern which really doesn't make sense, then it should inform you that there is something wrong, either wrong with your data, or there is something else, another factor which we are not capturing within the data set, okay, to explain that particular pattern you are observing. Yeah, let me take one or two questions on at this point before I continue. Let me have some one or two questions. Let me have questions, please, before I continue. Okay, before we go to the practical section. Theoretical model, as we all know, is that y, the data, is equals to beta naught plus beta 1 x plus some error, okay? So that is the theoretical model. Now, where y is your dependent, your x is independent, beta naught is your y intercept, beta 1 is your slope, and epsilon, the error, okay? And of course, our slope is the beta naught is indicated by the diagram there, which is the slope of the linear model. So which means as an assumption, there should be a linear pattern between your x and your y before you run what? A linear regression modeling. Very important. And we also assume that errors are, the expectation of our errors, okay, is always going to be zero because the errors are around what? The I mean the line, the linear path, okay? Go. So when we find the expectation of the errors around the straight line, we are going to get zero, and the variance of our error is also going to be what? Equal to sigma squared. So now, based on the least square approach, this is the derivation, okay, based on the least squared formula, we can clearly see that our beta 1 can be provided as what? M summation x y minus summation x times summation y over n summation s squared minus summation x all squared, which we know that is basically, in other terms, that's the covariance of xy over the variance in x. Okay, whilst beta naught is y bar minus beta 1 x bar. Now, and the resulting model, which we generate, okay, the output that we generate from your SPSS is always in the form y estimate is equals to beta naught plus beta 1 x. So all we need to find is our beta naught and then the beta 1 to write out the model of the process, okay, of the distribution. Good. Now moving on, this is a demonstration. Like I said, the emphasis is on the practical session. But I know you've done even more than what we are teaching here into depth, and you've done a lot of theory. So our emphasis will be on the practical session. But let's just touch on this example. So this is data on diastolic pressure, okay, for blood pressure for 5 individuals, okay. Of interest is the relationship between what? An intervention. So it says the following data are diastolic blood pressure measurement taken at different times after an intervention for 5 people. Now, for each person, the data available included the time of measurement and the diastolic blood pressure level. So we are interested in the two variables, which is the measurement, the time of measurement, and diastolic blood pressure. Okay, so this is the data we have. And as usual, what you need to find is your S square, your Y square, your XY, sum them up, find your beta naught, find your beta Y. Okay, good. So you find your beta 1, as we already saw. And then once you estimate that, you get minus 0.28. Okay, take note of that. So beta 1 is minus 0.28. And once we estimate the intercept 2, we get 70.4, okay, for our intercept, which means that the equation or our model becomes what? 70.4 minus 0.28x. Okay, good. And we all know in the interpretation of it, this simply means that when x increases by a unit, okay, so let's say if x equals to 1, then we are going to have a decrease of what? This coefficient in the value for y. If s goes to 2, it will be this times 2. Okay, so it means it's going to decrease further by the same coefficient. So in our interpretation, we say that so interpreting these are results here, we'll say that for a unit rise in what? Your independent value, y decreases by what? 0.28. Okay, so for a unit increase in y, in x, y decreases by 0.28. In other words, because this is the slope, this means we have a negative relationship between your diastolic blood pressure, okay, and the time. Yes, in other words, the graph or the data point we have here will be scattered in this form. So, which means that the slope of such a line will be negative. That is why we are getting this negative slope out here. Okay, whereas your intercepts, like we said, is going to be at 70.4 up here. Okay, good. From the linear model, this is what basically the model is talking about. Now, moving on to, I'm going to jump some few slides, though, just to explain certain things to you. Now, when we come to, these are SPSS output for the same data we've just seen. And if you look here clearly, this is the intercept we just saw, which is, you saw the model was y is equal to what? 70.4, okay, minus 0.28x. Yeah, so this is the model we saw earlier. And if you compare this clearly, we said this is a beta naught, okay, or in the earlier model you saw A, okay, minus beta 1 x, okay. So this beta 1 here is the coefficient of you see your independent variable is time, okay, so this is it. So the coefficient of time is what you are seeing in the model here, which is a negative 0.28. Please observe it carefully. Okay, so that is the coefficient, negative 0.28. It appears in the model. And then once again, when you come here, this is what? 70.4 over here. Okay, so that is the constant, which is the coefficient of the model. Okay, estimated. Good. Then another thing we need to take note of is, you see, in every linear regression, as you are aware, you need to first test the overall significance of, let's say, independent variables or variables toward the prediction of y. That's the first step. Okay, so it's always step one here, and that is done using what? The ANOVA table. Okay, so ANOVA table is to test the overall significance of your predictors, of your independent variables. Okay, and it will always tell you, okay, the significance using the F and the significant values. And to refresh our memories, this value you are seeing here, this significant value here, is your p-value. Okay, it's always your p-value. So the value generated by the statistical software will always be your p-value over here. Okay, now how do we compare such values with your alpha value? Okay, and again, let me mention that the default value for the statistical software is alpha of 0.05. Okay, alpha of 0.05, which means 95% confidence interval. Okay, 5%, okay, significance. Good. And we all know that in comparison, anytime that our p-value, okay, is less than an alpha value, then we conclude that the test is significant. Okay, good. The test is significant. So significant in the sense that we would have to reject what? Our null claim. The null claim always talks about something equal to 0. Okay, yes, and in this context, because we are talking about the relevance of the predictors, okay, the claim will be they are not significant predictors. The null will be predictors, the betas of the predictors are not significant in predicting the variation in what? In y. And your alternative will be what? That they are significant. Okay. Now, in this context, we can clearly see that our p-value here, okay, which is 0.213, is far, far, far greater than what? 0.05. So in that case, we can only conclude on non-significance. Okay, so non-significant. Okay, which means that we are going to stick with the null hypothesis. Once it's non-significant, we'll stick with the null hypothesis. We state that what? Your predictors are not relevant toward the prediction of the diastolic blood pressure. In other words, time is not relevant toward the prediction of what? Diastolic blood pressure. Good. So that is for the interpretation of what? Our ANOVA table. Now, what next? The next thing to do is to test the significance of the beta you estimated. Okay, whether your beta i's or your beta j's are equal to 0 or they are not equal to 0. So bj's are not equal to 0. Okay, good. And in this case, our bj, let me just write. So h naught is the first one. Okay, and then ha is your alternate hypothesis. Okay, good. So once again, you conclude based on what? On your alpha and the p-value, which I've just explained. Okay, and we all know that yes, in this case, bj, we only have one predictor. Okay, so we are just testing if the coefficient the coefficient here, okay, on the beta is significantly different from 0. If it's 0, then it means that in the model was y is equals to what? Let me just use the general model. So a plus something, a plus the beta times x. So if the value, you test the value of beta and it's 0, then it means that 0 times x will go to 0. So once again, the independent variable is not important in predicting your y. You understand? We can use your time to predict y. We've already stated that in the ANOVA, okay? But we want to ignore those results and then go into the modeling to see what the modeling will also tell us, okay? So once again, you test this hypothesis. This is the hypothesis we are testing. And of course, you test the significance of your beta using the t-test, okay? And the t-test looks at what your beta I or your beta J, okay, minus 0 over the standard error of the estimate. Okay, good. So we have the standard error of estimate here, which is 1.77. Okay, good. And once you do the computation, minus 0.28 divided by 1.77 will give you negative 1.578. Okay, that is how you get your t statistic. Okay, good. Then the question is, what next? Then you find the computer generates the p-value for you as usual. So we are going to use this p-value to compare with our alpha value. And once again, we can see a p-value of 0.213. You see, it's the same p-value we are having in the F statistic. Good. So this p-value is again greater than the alpha value of 0.05, okay, which suggests to us the need toward or which suggests to us we cannot, the test is not significant, meaning we cannot reject what? The null hypothesis, okay? So we fail to reject the hypothesis, the null hypothesis. And that also suggests that what? Beta 1, okay, the coefficient of time is equal to 0. If it's equal to 0, then like I explained, it is not relevant toward the predicting of diastolic blood pressure. Good. Then finally, in running a model, you also need to talk about what? The measure of accuracy, okay, like I said in the introduction. And that is given by a coefficient of determination, okay, good, which is your R square. So the R square value, the coefficient of determination, talks about the amount of what? Variability in diastolic blood pressure, which is what? Predicted by time, okay? Good. And clearly when you come here, your R square value is 0.454, okay? This simply means 45%, about 45.4%, okay, of variation, okay, in diastolic blood pressure is predicted by what? Time. In other words, we are saying that if we are going to base on time, then the level of accuracy of that model, the model we just predicted, is about 45%. And nobody wants to dwell on a model which is less than 50% accurate. Okay, good. So as a threshold, your R square value should exceed. Okay, R square should always exceed 50%. 50-50 chance, at least, for us to be sure that we can utilize this model. Aside that, such a model is not good enough for what? for any predicting or forecasting purpose. Good. Now, if the yeah, so clearly the concept of running linear regression modeling has been explained, and whatever we need to understand to has been explained. The only part is we are left with is how to access the model fit for the predicted values. Now let's go back to SPSS and then conduct a test based on our economic data. Okay, a test, and of course, before we do that, let's just examine our correlation table to decide on what we want to be our dependent variable in the modeling. So we can say that GDP, of course, that is a multidimensional factor. So these other factors will all come in there to affect the GDP. And it seems to have correlation with CPI, with unemployment rates. And CPI also seems to have something to do with unemployment rates. Good. So let's run a model. First, we are going to include all variables within the model and then see the outcome in our regression model. So let's go. We go to analyze, go to regression, and then go and select linear regression. And then we select our dependent to be GDP in this case. Let's have IR and the other predictors in there. Then for now, we are not going to do any prediction. We want to see the model, and the model fits for the data. So let's and see the output. Good. So the first thing we have here, this is quite an interesting model. It's very, very interesting. So the first thing we have here is ANOVA for the overall fit of the model, giving the three predictors. Sorry. So we can clearly see that predictors included in the model are significant toward predicting the observed pattern, right? Good. Now, the next thing we observe here is we have an R-square value which is very high, explaining about 81% of variability in the GDP. And of course, the adjusted R-square is high of 0.72. Good. Then we go to the test for B-test. So the coefficients for our model. So here we have GDP. So GDP, let me see if I can use a text. So we have GDP, equal to our constant is not significant, but so far the only significant variable we are observing there is for CPI. So we have CPI, and the coefficient of CPI there is what? 170.8220. If we're going to include a constant, right, that of course constant is not significant in this case, but assuming we're including that would have been your beta naught, which is 725 points. 364, okay, plus that. So this would have been our model, okay, if our constant was also significant, right? So in other words, we are saying that both interest rates and then unemployment rates, okay, are not um, required in predicting this. But let's do this. I think we need to, because most of the times you have high relationship between some of these economic variables. So we need to go back and then include them stepwise, okay, to be sure that we are not having multi-collinearity between IR and UR, okay, which is resulting in both of them being non-significant. So let's go back, rerun the analysis. So this time I'm going to skip one of these variables, okay, at a go, or you can use stepwise, okay, regression method, okay, good, either stepwise or a forward regression method. So let's see the outcome step by step. So in the first model here, we have CPI, which is our R squared is 0.771. Okay, and CPI is highly significant, and our constant is very significant here. You see, so the model with only CPI, okay, gives us a very good fitted model with a significant constant as well. Good. Now let's go down. Okay, so which means that clearly the two variables are still excluded from the model, okay, which means both IR and UR are not relevant in the prediction. If they were on a step-by-step basis, we'll realize that probably one of them is significant, okay, toward predicting the variability in our model. Okay, here you can see adjusted R square is 0.742 as compared to adjusted R squared in this case, which is 0.719. Okay, so which means that the final model we have down here is a far better model than the previous model. Okay, good. So it means that we can have we have our best model, okay, being what our GDP is equal to, we have -173 92.941, okay, plus our beta one, which is 149.384, okay, and we have CPI, okay. This is a very good model, accounting for close to 80% operation within the GDP, okay. So which means if we have to predict the GDP per the data we have at hand, right? You know, along the line we said there were some problems in the data we had, but per the data we have at hand, this would be the best model, okay, for predicting the outcome. Good. Now in class next week, we will be doing the prediction. We'll run the prediction and then try and do some model assessment of it, because you will need these things for your project work eventually, okay. Good. So basically this is how we derive the regression model in SPSS. If there are any questions, you can ask. Yeah, and let me start with the first question. Somebody asked,